Hello, my name is Marcel Böhme, and I'm a faculty member at the Max Planck Institute for Security and Privacy, and also an adjunct at Monash University. And this video is about our recent paper at ICSI 2022 on the reliability of coverage-based fuzzer benchmarking. This work is in collaboration with Laszlo and Jonathan of Google, who work on a fuzzer benchmarking platform called Benchr. So what is our problem? Suppose you have a couple of fuzzers and a program, and you run all of these fuzzers on your program, and none of those fuzzers finds any bugs. How do we know which fuzzer is better? Which fuzzer has the highest potential of finding bugs? Right? So firstly, it is good that no fuzzer finds a bug, right? That's a good sign. The program might be less likely to have any errors if all of those fuzzers find no bugs. But then again, any non-functional fuzzer finds no bugs either. So what a fuzzer does is it essentially generates inputs for a program and then sees that any of these inputs that it generated crashes the program. Inputs that were generated can also be called a test suite.
Okay, then the question is, how do we know which fuzzer-generated test suite is better?
We measure coverage. And let me say, as a fuzzer covers more code, it also finds more bugs, right? That makes sense because you cannot find bugs in code that is not covered. Right? So that example of a non-functional fuzzer that generates no inputs, it would not only not find any bugs, it would also not cover any code, and therefore not find any bugs in that code which is not covered. Right? So then the question is, how strong is that relationship between coverage and bug finding?
This question of the relationship between coverage and bug finding has been studied since the 1980s. And results have been contradictory. So here I have two papers, both from ICSI 2014. The first paper is called Coverage is not strongly correlated with test suite effectiveness.
So correlation is simply the strength of the relationship. And the observation is the test suites that achieve more coverage find more bugs only because they're bigger. Right? So as test suite size increases, they cover more code, but they also find more bugs, just because they increase in size. At exactly the same conference, ICSI 14, another set of authors published the opposite result. Indeed, there's a strong correlation between the code that is covered by a test suite and the bugs that are found by the test suite, but it doesn't matter whether the test suite is bigger or not. Test suite size is not a concern. So obviously, these are contradictory results. And so 6 years later, another set of authors wanted to investigate this contradiction, right? So something is wrong. Either test suite size is important or it's not important. We have to resolve this contradiction. And what they found is that test suite size does not matter, and here in yellow, and that there's indeed a strong correlation between coverage and the ability of the test suite to find bugs. So what we do is we did our experiments, but instead of using developer-generated test suites, we used fuzzer-generated test suites, right? And indeed, we find a very strong correlation. As the fuzzer covers more code, it will also find more bugs. And as you see, they're almost straight lines. The relationship is very strong, right? So here's again quantitatively 0.999 means very strong correlation. Right? Okay. Now we know there's a very strong correlation for fuzzers between the coverage achieved by the fuzzer and the number of bugs found. But then folks in fuzzing are not really convinced by that, right? So the recommendation in the work that is authoritative on fuzzer evaluation, we hear that we cannot compare two or more fuzzers in terms of coverage in order to establish one as the best fuzzer in terms of bug finding. We can't just use coverage as a substitute. So again, we have a contradiction, right? So we have a very strong correlation, and this intuition, we shouldn't see this correlation. And maybe that's also why the first paper was cited so often. It's evaluating fuzz testing. Everyone in fuzzing now knows these papers because they're always cited when you go to experimental design, because it kind of gives the standard for a sound experimental design in fuzzing these days. Run 20 trials, run for at least 24 hours, and use both coverage and bug finding results. So here's a little bit of an explanation. So surely showing an improved code coverage would indicate an improvement in fuzzing. Right? This makes sense. However, there's no fundamental reason that maximizing code coverage is directly connected to finding bugs. Right? Even if we assume that coverage and bug finding is correlated, that correlation may be weak. And the citation is to the first work that establishes there's no strong correlation between coverage and test suite effectiveness. And as such, a substantial improvement in coverage may yield merely a negligible improvement in bug finding effectiveness. Right? So they don't believe that strong correlation. And now the question is why? Right? So this is essentially the starting point for our paper. Why do we see this strong correlation? People find very strong correlations, but somehow people are not convinced that you can simply substitute one for the other. And the answer is they simply looked at the wrong statistical device to assess this question. And the correct statistical device would be to measure agreement. And so here's a paper from biostatistics, which explains exactly why. So these are common pitfalls in statistical analysis. And we have been doing this in software testing for many years. We have looked at correlation and not at agreement. Okay, so what do they say about correlation and agreement? Now, correlation refers to the presence of a relationship between two different variables, right? Is there a relation between coverage and bug finding? Of course, we have established this relationship by saying that if you do not cover something, you cannot find any bugs. There must be a relationship, right? And in fact, they're supposed to measure the same thing, right? Coverage is a proxy measure of bug finding. And things that are instruments that are supposed to measure the same thing, of course, must correlate, right? And we explain this in an example later. So two sets of observations, which are highly correlated, may have a poor agreement. However, if the two sets of values agree, they will surely be highly correlated. So suppose we have two instruments to measure some kind of value in a fluid, like here, acidity. A strong correlation means as the acidity in the glass increases, both instruments will also indicate an increase in pH values, the measures of acidity. As acidity rises in the ground truth, the measurements of that ground truth will also show an increase. So there's a strong correlation between the measurements of both instruments and the actual ground truth. Okay, weak agreement means if you take both instruments and you have like a couple of different tubes with different levels of acidity, and you take these two instruments and kind of rank them in terms of their pH values. A weak agreement means that they may rank these tubes differently. One gives this ranking and the other one gives a different ranking. This is the difference between correlation and agreement. Moderate agreement, or even weak agreement, means that we cannot reliably substitute one instrument for the other. So that's what we did. We measured agreement for fuzzers when we ranked them in terms of their coverage achieved. And then again, we ranked them in terms of their bug finding. And then we would simply plot this matrix here. So this is on the left-hand side, we see after a 1 hour campaign. And on the right-hand side, we see it for a 1-day campaign. And what we can directly see is that there is no straight line, right? So the best fuzzer in terms of coverage may not be the best fuzzer in terms of bug finding. There, you see almost random noise. Here is the case where you have the worst fuzzer in terms of coverage being the best fuzzer in terms of bug finding. Okay, so what is our experimental design? So what we do is we minimize threats to validity, and we do that using a so-called post hoc bug identification instead of a predetermined ground truth benchmark. And we'll talk about these threats to validity at the end of this talk. But what we essentially do is, instead of taking a benchmark where we know how many bugs exist in that benchmark, either by injecting these bugs ourselves or by knowing that there is a certain number of bugs in this code through previous testing efforts, we do not use such a ground truth-based benchmark. Instead, we run these fuzzers on arbitrarily chosen programs. So we have chosen them to be more likely to contain bugs, just to be more economical. but we do not know how many bugs there are. We run these fuzzers for 23 hours and then use a combination of automatic and manual deduplication. After fuzzing, we get some 350,000 generated bug reports. And then we run a tool from ClusterFuzz, which is being used at Google to classify these crashes into unique bugs. And so this ClusterFuzz deduplication is essentially battle tested, so because they actually use it. So ClusterFuzz runs more than 500 different open source projects and most applications at Google for fuzzing, and it automatically issues these bug reports. And so if it would be very noisy, nobody would use ClusterFuzz. After this process, we have 509 different unique bugs. Okay, so automated deduplication wasn't enough. We also analyzed these bug reports and again manually deduplicated these bugs. And this was using 2 professional software engineers and arrived at 235 unique bugs. Okay. So what we use is a fuzzer benchmarking infrastructure called FuzzBench. And FuzzBench automates the entire evaluation. It already has a number of fuzzers, and we use all of those fuzzers at the time of writing of the paper. But instead of using the programs that existed at the time of writing, we used that bridge to OSS Fuzz, which is another fuzzing platform, which has a lot of open source projects, more than 500, as I said earlier. And we just randomly chose these programs. I mentioned earlier, ClusterFuzz and OSS Fuzz have these automated bug reporting platform. So we know historically for which projects more bugs were reported. And then we simply chose a number of programs, 24 programs to be exact, that have historically more bugs. Okay, so this is total 13.2 million lines of code. And we immediately see that for 20 to 30% of the programs, we do not find any bugs, right? So this is a problem of a post hoc study. We do not know whether we actually find any bugs, but the benefit is we do not have any confirmation bias, no selection bias, no other threats to validity. We also provided all data and the analysis and the entire infrastructure online. And so here are some of the results. We rank these fuzzers in terms of coverage and in terms of bug finding. And then we get this metrics. And then we can compute Spearman's rank correlation. So we can compute the correlation on these ranks. And here's an interpretation of these values. And here's the table showing the correlation between branch coverage and number of bugs found. We can also do the same with time to error. The fuzzer that finds the first bug fastest is the rank 1 fuzzer in terms of time to error. Agreement is even smaller. But ranking is a problem, right? So in ranking, what happens is some differences between fuzzer ranks might not be statistically significant. So some might have the same rank. So how do you break these ranks? Currently, we break them randomly. So what if we, instead of looking at ranking, we look at superiority? So we've been given only 2 fuzzers. And then we require that these 2 fuzzers exhibit a difference in terms of coverage and in terms of bug finding that is statistically significant at a certain p-value, right? So a common value for p is 0.05. That is often thought to be statistically significant. We already see that among all fuzzer pairs, only 33% of these fuzzer pairs satisfy this condition that the difference must be less than equals 0.05 for both the difference in terms of coverage and the difference in terms of bug finding. And kappa, Cohen's kappa, it has a different interpretation. So suppose we have 0.53. 0.53 means a weak agreement, okay? The same for time to error, 0.488. And as we increase statistical significance, we of course reduce the number of pairs for which this is satisfied, but we see agreement go up. So in this specific case, we see a strong agreement on the superiority of a fuzzer when we check superiority in both branches in terms of number of bugs, and require statistical significance to be less than 0.001, which is a really strong requirement, right? For time to error, we see a much smaller agreement again. 0.553 is still considered a weak agreement.
Okay, we know that we might get a strong agreement if the differences in terms of branch coverage and the number of bugs found is statistically significant at high p-values. But in practice, we can't really measure the statistical significance of the differences in terms of number of bugs found. So what if we only require the difference in terms of branch coverage to be significant?
And again, we see only a weak agreement, a very weak agreement. In fact, 0.3 is a minimal agreement, right? We also provide two other measures of agreement on superiority. One is called disagreement proportion, and the other one is the Spearman's rank correlation. If we classify each fuzzer pair into one fuzzer is superior, the difference is not statistically significant, and one fuzzer is inferior. So using this classification, we can now easily find the agreement in terms of Spearman's role, but it also include all of the evidence, even the evidence from fuzzers where the difference is not statistically significant. Again, the interpretation is we see a weak agreement. Okay, let's talk about the threats to validity. Is there anything that could go wrong with the setup that we have in our experiments that we don't see, that we only see a moderate agreement because of some problems in our experimental design? So let's analyze this a little bit. We chose 23 hours as the length of our campaign. Can we look at how does agreement increase as the length of the fuzzing campaign increases? And what we find is not really. So here we see plots for different values of statistical significance and for different measures of agreement on superiority, how agreement behaves over time. And the best case interpretation of these graphs is agreement kind of stays constant over campaign length. It does not increase. So what about the number of trials? So many fuzzing experiments use about 10 trials. The recommendation is to use 20 trials, and that's what we did. Maybe 20 trials is too few to see an agreement. So here we see the number of trials, agreement over the number of trials, and agreement indeed increases as we increase the number of trials. So it's important to run at least 20 trials here. So then we went and investigated what happens if we increase the number of trials to about 60. And what we see is that agreement kind of saturates. So we don't really need to do any more than 20 trials, because of course, if you do 3 times more trials, you need 3 times more compute, which might not be very practical. So 20 trials seem to be fine. Another problem, another threat to validity could be the generality of our cells. So how does agreement behave as the number of subjects increases? So this is what we see here. And what is very obvious is while agreement stays about, on the average, stays about the same, the variance of the agreement is very high for a low number of subjects, right? So if you happen to do any experiments with about 3 or 6 different programs, you might see a very high agreement, or you might see a very low agreement, but it's only due to the variance in your experimental setup. So we started with 24 programs, and 17 of which we, because of our post hoc analysis, and 17 of which we only find bugs. And this seems to be reasonable. The agreement doesn't vary a lot at about 15 randomly sampled programs. We observe a moderate agreement on the superiority or ranking of fuzzers. If we compare fuzzers in terms of coverage or in terms of bug finding, there's only a moderate agreement. Only if we require the differences in coverage and bug finding to be highly statistically significant, we actually observe a strong agreement. And so what does it mean? You can substitute coverage for bug finding only with moderate reliability. It's only moderately reliable. Okay, so now we know about the challenges of coverage-based benchmarking. What about the challenges of bug-based benchmarking? In fact, 2 of the 3 reviewers asked us why we not simply use a ground truth, why we use this very difficult post hoc analysis where we need to manually deduplicate And so we build a very strong and a very large argument in our rebuttal, which is essentially the following. So before we talk about ground truth-based evaluation, let's talk about the golden way of evaluating a set of fuzzers. So what we would do is we would choose a random and representative sample of programs. Representative means programs that people would be interested in fuzzing and finding bugs in. For instance, security critical programs or something like that. And then you would fuzz them. So if you had unlimited resources, this is the evaluation that you have. But quickly you would find that bugs are very sparse, fortunately. But the problem is if you don't have enough resources, this means there's no statistical power in the results, in the evaluation. So it's not very economical. Instead, people previously suggested, and many previous studies were based on a mutation-based evaluation. So you take a real program that you're interested in finding bugs, but instead of expecting real bugs, you simply inject synthetic bugs into these programs. This is, of course, more economical because we already know that we can find bugs in these programs. We can inject as many bugs as we want, right? The problem, though, is that many people don't really believe that synthetic bugs are representative of real bugs. Of course, this is a recent and hot topic in the community. Okay, so apart from these synthetic bugs that we can control and simply inject, there have been some efforts to curate real bugs. So you take a program and simply look at the bug reports for these programs and then build a benchmark from these real bugs. Of course, this is more economical because you already know that you can find bugs. It's also realistic. Unlike synthetic bugs, these are real bugs. And it provides some kind of objective ground truth, right? It's not me who introduced these bugs, but these bugs actually existed. But there are several problems with ground truth-based evaluation. And these problems might not be very obvious. So the first is survivorship bias. So this benchmark that is curated is consisting of a set of real bugs that we already know how to find, right? So if you have a fuzzer that can find bugs that we do not know how to find, because we're only looking for a specific set of bugs that we already know how to find, this fuzzer, which is actually truthfully better, will appear worse. Right? On the other hand, fuzzers that actively contributed to the original discovery of these bugs will appear better. Right? So this is called survivorship bias. That's the first problem. The second problem is experimental bias. In order to be more economical, researchers would port bugs from previous versions into one single version. So a program only has a small number of bugs at any point in time, but in their history, they might have had a lot more bugs. So what researchers do in order to increase the number of bugs in this given program, they reintroduce these bugs into a single program. And the problem of this is that you artificially introduce bug masking and bug interaction effects that didn't exist before. The third problem is called observer expectancy bias. So researchers would sometimes translate bugs into if statements or assertions that would then represent the bug trigger condition. And this would simplify bug counting. It would also streamline the way fuzzers indicate bugs, right? You would have the same oracles for all bugs. If you reach that position in the code, the bug is triggered. But it also enforces a relationship between coverage and bug finding. And this is exactly this relationship that we are investigating in our study. The fourth problem is confirmation bias. So when you have a ground truth-based evaluation, researchers might feel enticed to iteratively and unknowingly tune their fuzzer to that benchmark. The last kind of evaluation that we chose to do is called post-hoc bug-based evaluation, where you would try to maximize the bug probability in random representative samples of programs. So this is essentially helping you to be economical. But instead of expecting a certain set of bugs, you would identify and deduplicate bugs after the campaign. And this would minimize bias, these different sources of bias. The problem is it's of course less economical. We had to actually manually deduplicate these bugs. And we fuzzed programs that didn't actually have any bugs. So, okay, coverage-based benchmarking is not very reliable, but bug-based benchmarking is not easy to get right either. So when we submitted the paper, a reviewer after the rebuttal wrote a meta review and told us about the role of this paper in informing experimental design and future fuzzing research. And this reviewer was very concerned that we would say that you should only use bug-based benchmarking. But instead, what we should say is that we need a more holistic fuzzer evaluation. And particularly, we should describe other efforts that call for a more holistic fuzzer evaluation. So we synthesized a set of recommendations based on previous work, based on our own results, and based on our own experience. So here are those recommendations. You should select at least 10 representative programs, and you should repeat each experiment for at least 10, better at 20 times. You should select real-world programs that are typically fast in practice, and increasing this representativeness also improves generality. And if experimental cost is a concern, then prioritize programs that are more likely to be buggy. Third, you should select a baseline that you actually extended to implement your technique. And then you should ensure that conditions under which you run all the fuzzers that you're comparing are equivalent. And this improves construct validity. And because you select the baseline which you extended to implement your technique, you can attribute precisely observed improvements to your technique that you implemented. Optionally, if you want to compare to the state of the art and establish your own tool as part of the state of the art, you can do that. But you should note that the improvements that you observe can be due to engineering differences. Right? So different programming languages, different design decisions. So you should always have a fair baseline which you extend. Another suggestion that we have is to consider a training set when you're developing the fuzzer and a validation set when you're then actually evaluating that fuzzer, for instance, an independent benchmarking platform. And this would reduce overfitting and also mitigate this confirmation bias. Next, you should always have a statistical analysis. Fuzzing is inherently random, and statistical analysis allows you to assess the magnitude of the differences between two fuzzers and the degree to which these differences are explained by randomness. 6, you should always measure and report both coverage and bug-based metrics. Right? And you should always use the same measurement tooling and procedures across all fuzzers. And this improves construct validity. 7, you should discuss potential threats to validity and your strategy to mitigate these threats. And this would help the reader to assess the validity of the claims, key claims in your paper and the results. And lastly, you should always ensure that your experiments are reproducible. You should publish your tool, your benchmark, your data, your analysis, and report specific experimental parameters. We strongly believe that reproducibility is the foundation of sound scientific progress and also facilitates replicability, of course. Okay, so what did we talk about today? Firstly, we actually started from somewhere totally different. Right? Our initial question was, suppose that none of our fuzzers finds any bugs in our program. How do we know which fuzzer is better? Right? So the typical answer is we measure coverage. Right? So if we don't have any bugs, we measure coverage. But we actually observe only a moderate agreement on superiority and ranking. So if you want, you can substitute coverage for bug finding, but only with moderate reliability. Coverage-based benchmarking should always be accompanied by bug-based benchmarking. But bug-based benchmarking comes with its own challenges. So all in all, we provide 8 recommendations for sound fuzzer benchmarking. Thank you very much. I hope you enjoyed the rest of the conference.